In 2023, a Harvard astrophysicist led an expedition to the Pacific Ocean floor, not to study marine biology, not to survey geological formations, to search for fragments of a machine. Avi Loeb, chair of Harvard's Astronomy department and founder of the Galileo Project, had calculated the trajectory of a meteor that entered Earth's atmosphere in January 2014 off the coast of Papua New Guinea. The meteor, designated CNEOS, the 8th of January 2014, was confirmed by United States Space Command as moving faster than 95% of all stars in the solar neighborhood, implying it had originated outside our solar system entirely. When the object entered Earth's atmosphere, it produced a fireball and disintegrated, scattering material that fell into the Pacific Ocean. Loeb raised private funding, chartered a research vessel, and used a magnetic sled to sweep the ocean floor along the calculated trajectory. What the team recovered were tiny spherules, microscopic metallic balls, whose composition did not match any known meteorite type in the scientific catalog. The materials had unusually high concentrations of beryllium, lanthanum, and uranium, an elemental ratio the researchers called below U that did not fit any natural geological or astrophysical process they were aware of. The Galileo Project is currently continuing the analysis of these spherules. The results are not yet published in final peer-reviewed form, and Loeb has been careful to say that the unusual composition does not prove artificial origin, but he has also said clearly that he cannot currently explain it using known natural processes. The first confirmed interstellar object to impact Earth, recovered from the ocean floor, with anomalous material composition. That is where the investigation currently sits. This is the context in which the question of whether alien robots could already be on Earth is no longer purely speculative. Not because the question has been answered, but because serious scientific institutions with serious funding have decided the question is worth asking systematically and have begun doing so. The Galileo Project, with its network of multi-sensor observatories collecting data on millions of aerial objects, its study of interstellar meteors, and its ongoing analysis of UAP reports, represents the first sustained, data-driven, institutionally legitimate effort to search for alien technology in Earth's vicinity rather than at interstellar distances, and the specific hypothesis it is designed to test is exactly the one this conversation begins with. What if something is already here? The scientific logic behind why something might be here traces back to the same mathematics that drives the von Neumann probe hypothesis. If a civilization capable of building self-replicating robotic explorers existed anywhere in the galaxy at any point in the past several billion years, those machines would have had more than enough time to reach every star system in the Milky Way, including ours. A probe that arrived in our solar system could have done so millions of years before human beings evolved. It could have taken up a position anywhere in the vast space of our solar system and simply waited, powered down or operating at minimal energy, for conditions to change. The specific condition worth waiting for. From the perspective of a probe designed to monitor for the emergence of technological civilizations, would be the appearance of radio frequency emissions from a planet's surface. Earth began emitting detectable radio signals roughly a century ago, which means that if any probe was within 100 light-years and listening, it would have received confirmation of our technological development between 1 and 100 years ago, depending on its distance and the strength of the signal it was designed to detect. The question of where such a probe might position itself is one that physicists Paul Davies and Robert Wagner at Arizona State University addressed in a peer-reviewed paper published in Acta Astronomica. Their argument was that the moon is the single most logical location for a long-term monitoring artifact in our solar system. The reasoning was specific. The moon has no atmosphere, no weather, no erosion, no plate tectonics, and no geological processes that would bury, alter, or destroy a surface object over timescales of millions of years. An artifact placed on the lunar surface tens of millions of years ago could still be sitting there, unchanged, in the same condition it was left, covered by at most a thin layer of micrometeorite dust that accumulates at known rates and could be calculated precisely. The lunar interior is even more stable. Lava tubes, underground tunnels, formed by ancient volcanic activity, provide environments that have been sealed and protected from the surface environment for billions of years. Davies and Wagner noted that lava tubes are particularly interesting because anything placed inside one before the tube sealed would have been protected from every surface process for the entire subsequent history of the moon. They proposed a systematic search of existing lunar reconnaissance, orbiter imagery for geometric anomalies, regular shapes or patterns that natural geological processes would not produce, and acknowledged that the odds of finding anything were low but that the cost of looking was essentially zero since the data already exists. Penn State researchers Jacob Hack-Misra and Ravi Kumar Kaparapu extended the same argument to Mars the following year. Their logic was that Mars, while more geologically active than the moon, shares the same fundamental advantage as a hiding place. It is close enough to the inner solar system that any probe monitoring Earth would have it within easy range, and it is sufficiently removed from Earth's surface that any artifact there would be isolated from the biological and technological noise of the planet it is watching. Mars has polar ice caps that have preserved material for millions of years. Mars has subsurface environments where liquid water may still exist and where temperature and pressure conditions are more stable than the surface. And Mars receives less than a tenth of the asteroid impact rate per unit area that the inner asteroid belt does, meaning surface features can persist for far longer than on more geologically active bodies. But here is where the question specifically about Earth becomes interesting, and where the physics of concealment makes the problem harder than it first appears. Earth is the worst place in the solar system to hide something if you want it to remain undiscovered by the civilization developing on it. Every square kilometer of Earth's surface has been walked on, photographed, drilled into, or remote sensed at some level of resolution. The ocean floors are less explored, and here, the concealment argument has genuine force. The average depth of Earth's oceans is approximately 3,800 meters. The deepest point, the Challenger Deep in the Mariana Trench, reaches nearly 11,000 meters. The total area of the ocean floor exceeds 360 million square kilometers. We have directly observed a fraction of a percent of it. Any object resting on the ocean floor, in deep water, inactive, and with no electromagnetic emissions, would be essentially undetectable with current technology unless a survey vessel happened to pass directly over it with appropriate sonar equipment. The ocean floor is also geologically quiet in its abyssal regions. Sediment accumulates slowly. In the deepest plains, objects could potentially remain undisturbed for millions of years. The transmedium behavior, documented in military UAP reports, is relevant here in a way that most discussions of that behavior overlook. Multiple high-quality sensor recordings show objects transitioning between air and water, entering the ocean at speed without producing the impact signatures that physics demands from conventional objects. If some of these objects are probes, machines operating with some agenda in our solar system, then the ocean offers precisely the concealment properties that a long-term monitoring artifact would require. A machine capable of operating effectively in both air and water, moving between the two environments fluidly, would have access to both observation of the surface and concealment in the deep ocean as needed. The military reports describe these objects returning to the water after aerial observation periods. If that behavior is real, and if its origin is artificial and non-human, then the ocean is where these machines base themselves when they are not actively observing. The deep ocean is not the only concealment environment that deserves consideration. Earth's continental crust extends to depths of up to 70 kilometers in mountainous regions. The oceanic crust is thinner, typically 5 to 10 kilometers. Below both lies the mantle, which extends to depths of approximately 2,900 kilometers. Nothing we currently build can penetrate more than a few kilometers of rock. The deepest borehole ever drilled, the Soviet Kola super-deep borehole, reached 12,262 meters before the project was abandoned in 1992. Below that depth, the Earth's interior is known only through seismological inference. An object resting at depths below what any current technology can directly sample would be effectively invisible to every detection method we have except seismic wave analysis. And distinguishing an artificial structure from a natural geological formation using seismic data alone is an extraordinarily difficult inverse problem that seismologists have not solved even for known natural structures. The deepest subsurface life on Earth, microorganisms found at depths of more than 3 kilometers in rock fractures, demonstrates that complex chemistry can be sustained at depths well below the surface, in environments completely isolated from the biosphere above. Any machine using geological heat as a power source and positioned in the deep crust would be operating in an environment where liquid water, chemical gradients, and stable temperatures provide everything needed for long-term operation, and it would be completely, effectively invisible to everything humanity currently uses to observe its own planet. The counterargument to all of this is one that Avi Loeb himself acknowledges in his own writings. The prior probability that any of this is true is very low. The number of assumptions required for an artifact to be present and undetected is large. Each assumption multiplies against the others. A civilization had to exist and build probes. The probes had to survive interstellar travel. They had to arrive in our solar system. They had to survive billions of years of operation in our solar system. They had to position themselves in locations that our current technology cannot reach. And they had to remain inactive enough that we have not detected their emissions in any of our surveys. Each of these conditions individually is uncertain. Together they represent a chain of probability that most physicists would consider extremely unlikely. This is the honest scientific position, and it deserves to be stated clearly. What makes the question worth asking anyway is something that Loeb has articulated repeatedly in his published writings. The cost of conducting the search is low relative to the potential significance of a positive result. The Galileo Project's ground-based observatory network, the analysis of interstellar meteor materials, the systematic search for anomalous technosignatures in existing data, none of this requires the kind of resource commitment that would be unreasonable given the stakes. If a probe is here and detectable, finding it would be the most significant discovery in the history of our species. If nothing is found after a thorough search, the search itself constrains the parameter space of what is possible, and that is also scientifically valuable. And if the materials from the ocean floor recovered in 2023 turn out, when the analysis is complete, to have a composition that cannot be explained by any known natural or artificial human process, the conversation will move from theoretical to empirical in a way that changes everything that follows. That analysis is not yet finished. The results are not yet published. And the ocean floor, where an interstellar object came apart, thousands of meters beneath the Pacific, is still holding whatever it holds, in the same cold dark where it has been sitting since January of 2014.